Welcome to Sita Lakshmi Ramaswamy College. I'm Dr.S.Karthiga from PG and Research Department of Physics. So in this lecture video, I'm going to help you understand the Lagrangian and Hamiltonian mechanics, how they are useful in studying the dynamics of a system. So with this, we enter into the contents of the presentation. So I first briefly review the Newtonian, Lagrangian and Hamiltonian mechanics and tell you the advantages of Lagrangian and Hamiltonian dynamics over Newtonian mechanics. And then with a neat example and also a simple example, I'll illustrate the construction of Lagrangian and Hamiltonian, and from the Hamiltonian and Lagrangian, I'll illustrate you how to obtain the equation of motion. Once you obtain the equation of motion, by solving the equation of motion, you can get the solution or the state of the system. So also I wish to note that this Lagrangian and Hamiltonian is often asked in CSER problems. So this lecture video may be helpful for you to attend or solve problems that are asked in CSER. Let us now review the Newtonian mechanics. So the core objective of mechanics or dynamics or even physics is to understand the state of the system after a particular instant of time or future time. For example, the system may be a satellite or it may be a planet. So if you consider satellite, or after 1 hour, where that satellite would be. So after 2 hours, where the satellite would be and in which velocity it has to be moved. So these things can be calculated or predicted using mathematical models. So the Newton is the person who first give the mathematical model for a mechanical system. So that is the Newton's that is through the Newton's second law of motion, which gives a relation between the force and acceleration. So this is an ultimately a differential equation. So by solving this differential equation, you will get r of t, that is the position r, the position vector, the position r with respect to time. So what is the input that you need to construct this mathematical model is that the force, the total force acting on the system. So we need to list out all the forces acting on the system. Then you can construct the Newton's equation of motion. Once you solve the differential equation, you will get the position of the system. Position, not only position, you can get velocity and the other corresponding quantities easily from this solution of this differential equations. So while using this Newtonian mechanics, what is the difficulty that we face is that here we need to specify all the forces acting on the system. For example, consider the motion of a mass m over a ramp. So here the mass m is restricted to move only on the ramp, only along the ramp. So the motion is constrained. So the forces that acting on the system are two. One is the gravitational force and the other is the force exerted by the ramp over the mass. So the gravitational force is very easily obtained, it is known, but when you consider the force exerted by ramp over the mass is not that much easy to obtain, and this is one of the simplest problem. So if you consider some complicated problems, means the way to obtain constraint forces is very difficult. So this shows the inadequacy or disadvantages of disadvantage of Newtonian mechanics. So we look after other possibilities. So in the past, Lagrangian and Hamiltonian mechanics were proposed as an alternative to Newtonian mechanics. So what is the advantage of these two? Or we don't need to look after the constraint forces. The constraints are here overcome they are taken care of by the coordinates that are chosen for for studying the Lagrangian and Hamiltonian dynamics. And also the Lagrangian and Hamiltonian dynamics are concerned with scalars rather than vectors. So the mathematical simplicity is also there in this Lagrangian and Hamiltonian mechanics. So with this, we'll move on to Lagrangian mechanics. So Lagrangian mechanics, the basis is to construct the generalized coordinates. These generalized coordinates help to take care of the constraints, and from this generalized coordinates you will construct the Lagrangian. So here q and q dot are the generalized coordinates, generalized position and generalized velocity coordinates, and from the Lagrangian, L is constructed from the difference of kinetic energy and potential energy. So once you obtain the kinetic energy and potential energy, the Lagrangian can be constructed. So once the Lagrangian is constructed, you can obtain the equation of motion, Lagrangian equation of motion, from the below equation, d by dt of dou L by dou Qj dot minus dou L by dou Qj equal to 0. So, here the problem is to find the generalized coordinate. So firstly we have to find the generalized coordinates. So these generalized coordinates are the minimal number of coordinates that should take care of all the constraints, and also that should describe the complete state of the system. So we can say generalized coordinates are the minimal number of coordinates that are required to specify the complete state of the system, which should take care of all the constraints of the system. So once you obtain the generalized coordinates, from that you can find the kinetic energy and potential energy. From that you can find the Lagrangian through the difference of kinetic energy and potential energy. So once the Lagrangian is obtained, so it is just a mathematics to find the equation of motion through the below equation, d by dt of dou L by dou Qj dot minus dou L by dou Qj is equal to 0. So this gives a set of second order differential equation, and while solving this equation you can find the state of the systems. So the only trickier part in this procedure is to find the generalized coordinates. So here you should be you should be careful that the constraints are taken care of properly. And also here you should remember that if you choose the coordinate system properly, means you can get you can take care of constraints very easily, and also the generalized coordinates will be minimal. So the choice of coordinate system, also you have to take care that the choice of coordinate system is suitable, and also you have to take care of the constraints of the system. So once the generalized coordinates are chosen, other things are just mathematical, just mathematics, so you can forward it very easily. So with this we now move on. With this, we move on to Hamiltonian mechanics. So, in the Lagrangian mechanics, we considered the generalized variables, which are the generalized position and the generalized velocity coordinates. In Hamiltonian mechanics, we are going to deal with generalized position and generalized momentum coordinates. So, the position and momentum coordinates are considered instead of position and velocity. So, just by replacing generalized velocity by generalized momentum, you can obtain Hamiltonian mechanics. So here you have considered the canonically conjugate variables in it. So the position and momentum canonically conjugate variables are considered in Hamiltonian mechanics. So it is useful in extending to other fields like quantum mechanics. It is useful in statistical mechanics and all. Also, as they are constructed in canonical variables, as they are independent, so it is useful in solving through canonical transformation. You can easily solve the differential equation. So in summary, you can say that the Lagrangian mechanics is considered in constructed in a configuration space, the space in which the position and velocity are considered as coordinate, and the Hamiltonian mechanics is considered in phase space, phase space in which the position and momentum are considered to be your coordinates. So with this, I'll illustrate how to obtain Hamiltonian. So the Hamiltonian is obtained from the Lagrangian itself through a Legendre transformation. So I have given the form of the Legendre transformation that need to compute Hamiltonian. So it is just summation over I equal to 1 to n pi qi dot minus L. So here you need to specify, you need to replace it velocity by momentum coordinates. How will you do that? So for that we can obtain the relation between P and Q dot from the Lagrangian itself, where Pi is equal to dou L by dou Q dot. From this expression you can obtain the relation between P and Q dot, so that you can replace all the velocity coordinates that are present in Hamiltonian by momentum coordinates. So finally, with the obtained Hamiltonian, you can obtain the equations of motion. So through this equation, the final q dot equal to dou h by dou p and p dot equal to minus dou h by dou q. So this is the procedure to obtain the Hamiltonian and Hamiltonian's equation of motion. So the firstly, to understand even Hamiltonian mechanics, you need to find the Lagrangian. So as I have told in the previous slides, you obtain the Lagrangian and find conjugate momenta. So you will obtain the relation between momentum and the velocity coordinates. So you try, then you do Legendre transformation of further Lagrangian. So here you will have the Hamiltonian will have some velocity coordinates. You try to replace all the velocity coordinate by momentum. So you will then you will obtain Hamiltonian function of position and momentum coordinates alone. From the Hamiltonian, you just construct the equations of motion. So once the equations of motions are constructed, so these are set of differential equation. You solve this differential equation, then you can obtain the solution of the system. So the key difference that you observe between the Lagrangian and Hamiltonian is, like in Lagrangian mechanics, you will have a set of second order differential equation, but in Hamiltonian mechanics, you will have first order differential equations. So we now consider a simple example, that is a simple pendulum, with which we try to understand how the Lagrangian and Hamiltonian can be obtained for a particular system, and how the equations of motion are obtained. So this is the system under consideration. Here you can see a mass M is hanged by a string of length L. So here the length L should be a constant. So this is the constraint of the equation. This is the constraint that you have here. So the motion of the mass M is restricted that it is hang over a string. So and that string length is constant. This is the constraint here. So we are going to study the motion of this pendulum through Lagrangian as well as Hamiltonian mechanics. So as obvious, in studying Lagrangian mechanics, the first step is to find the generalized coordinates, the minimum coordinates that are useful in describing the state of the system. So here, if you consider Cartesian coordinate, you can find the variables x and y are needed to describe the motion of the system at any particular time. So only by saying what is the value of x and what is the value of y, so then only you can say the state where the mass m is. So the state of the system is described by both x and y coordinates. Also, due to the constraint, that is this length is L is a constant, you can make a choice. So this x square plus y square will be always be L square. So from that you can obtain y is always minus root of L square minus x square. But this form is not a simplified one. So if you consider the coordinate system, polar coordinate system, you can find that this can be this is your radial vector. So this r, this help you to fix r as a constant, and the only coordinate that is varying is theta. So as I have told earlier, to construct generalized coordinates, you have to choose appropriate coordinate system. So by choosing an appropriate coordinate system, the problem can be reduced very well. So the same thing happens here. So rather than choosing Cartesian coordinate, if you choose polar coordinate, the problem is simplified. Here you have the generalized coordinate is only one theta, and it is the constraint equation is very simple where r is a constant. So I choose this coordinate system, this generalized coordinate, and proceed how to obtain the so as I have told earlier, with this generalized coordinate theta, you can define the state of the system at any instant of time. For example, you consider the mass M is placed at the position A. So I could say the state of this the system through theta. So for example, consider this rectangular triangle OAB. So apply the trigonometric relation, and you can obtain x as L sine theta and y as minus L cos theta. So just by defining theta, you can uh, mention the state of the system. So once you have obtained the generalized coordinate, the next step is to find the kinetic energy and potential energy. So you have obtained x and y. Just substitute in the form of kinetic and potential energy. Kinetic energy is nothing but half into m into x dot square plus y dot square, and the force that are acting on the system is the gravitational force. So it is obviously the gravitational potential that is need to be considered. So I consider gravitational potential, which is mgy. So you just substitute y, replace y by L cos theta, obtain the potential energy. From the kinetic energy and potential energy, you will obtain the Lagrangian. So once the Lagrangian is known, the equation of motion can be easily obtained. So as you have only one generalized coordinate here, so the theta is the generalized coordinate here, you will have only one set of equation of second order differential equation, that is you will have d by dt of dou by dou theta dot minus dou by dou theta equal to 0. So if you have multiple generalized coordinates, means you have multiple equations. So here, as we have only one generalized coordinate, one equation is there. So I find dou L by dou theta dot and d by dt of dou L by dou theta dot, dou L by dou theta. From this I obtain the equation of motion as theta double dot plus g by L sin theta equal to 0. This is obviously a non-linear differential equation. So if you solve this differential equation, you will get theta with respect to time at different time. So once theta is known, you can find the position of the system very clearly, as I explained in the previous slide. So with this, I now move on. So with this, I now move on to Hamiltonian way of solving a simple pendulum. So as I've told you earlier, even in the Hamiltonian dynamics, you need to construct the Lagrangian is the basis for construction of Hamiltonian. So I consider the Lagrangian that is constructed in the previous slide, and then I also find out the conjugate momentum coordinate. So which is obtained by p theta equal to dou L by dou theta dot. So this gives you the relation between p theta and theta dot. So you obtain the form of theta dot from this equation. So theta dot is nothing but p theta by ml square. This helps you in replacing the theta dot coordinates appears in Hamiltonian. So for example, so Lagrangian is there. The relation between p theta and theta dot is obtained. So the next step is to do Legendre transformation and obtain Hamiltonian. So I just do the Legendre transformation here, where p theta into theta dot minus L is the Legendre transformation. So I substitute Lagrangian here. So the Hamiltonian now contains theta dot and p theta and theta coordinates. But the Hamiltonian is need to be in theta and p theta. So just replace all the theta dot quantities here using the above equation. So you will obtain a Hamiltonian in theta and p theta, canonically conjugate variables. So with this Hamiltonian, you can easily obtain the Hamilton's equation of motion that are given in step 3. So theta dot is nothing but p theta by ml square, and p theta dot is nothing but minus mgl sin theta. So comparing the equation of motion that is obtained in Lagrangian, and with this you can find that in the Lagrangian it is you obtained a second order differential equations, but in here in Hamiltonian you obtain two first order differential equations. So are they different or same? This question may arise in you. So I am going to answer this. Just take this theta dot equation and differentiate it again. So you find theta double dot, which is nothing but p theta dot by ml square. So p theta dot is nothing but it is given the one of the other equation of Hamilton's equation of motion. So p theta dot is nothing but minus mgl sin theta. When you substitute it here, so you will obtain theta double dot by g by l sin theta equal to 0. This is the same second order differential equation which is obtained in Lagrangian mechanics. So what I conclude is, so whether you use Newtonian or Lagrangian or Hamiltonian, you will end up with same equation of motion, because the state of the system is not going to vary. The system going to evolve in the same manner. So the method you use to study the state of the system is going to vary. So Newtonian, Lagrangian, Hamiltonian are three different methods that are with three different mathematical formulation. You can say they are three different mathematical formulation that are help to study the state of the system. So ultimately the result is same, the dynamics is same, so the equation of motion would be same, so the mathematical techniques is different. So this I conclude my talk. So here we have briefly reviewed the Newtonian, Lagrangian and Hamiltonian mechanics with a neat example of a simple pendulum. I have illustrated how to obtain Lagrangian and Hamiltonian, from which you have obtained the equation of motion. So by solving this differential equation, you can obtain the state of the system with respect to time. So I hope this lecture video help you to understand how to solve problems in Lagrangian and Hamiltonian. Thank you so much. And I also wish you to read these books, Goldstein and Thornton Marion. And in Thornton Marion, there are number of problems were considered. So that may be helpful for you to solve, construct Lagrangian and Hamiltonian for various problems, like various complicated problems, and helps you to solve problems in CSR, GATE, or whatever be the competitive examination be. Okay, thank you so much. Thank you.